and I'm here to tell you a little bit about Talek, a private group messaging system with hidden access patterns. This is some work that was done between the University of Washington and Carnegie Mellon. Group messaging is everywhere, whether you see it specifically or not. We have applications today like chat, news feeds, calendars, even games and IoT. A lot of these applications can be modeled as a group messaging system, one where users deposit messages into a log, and users can subscribe to either messages or events, typically facilitated by some kind of cloud service. Now, today we have end-to-end encryption. So it is a well-known problem and a well-known set of solutions for encrypting the messages end-to-end such that the cloud service has no way of reading the contents of the messages themselves. And some examples of this would be things like Signal, WhatsApp, and iMessage. Now, a curious cloud can still log all of the network accesses and be able to determine statistical and do some statistical analysis on the message workload itself. And ultimately, what that means is that the communication patterns themselves become exposed. The cloud service can determine which users are sharing data, who is talking to who, when traffic is sent, how much data is sent, and sometimes potentially even allowing the adversary to infer the contents of the communications itself. Now, for vulnerable populations or activists or journalists trying to talk to their sources, this data is incredibly sensitive, and our goal is to design a system that can practically protect it. So Talek is a private group messaging system for sharing data through untrusted clouds. So what that means is that our goal is to hide both the contents of the messages as well as the communication patterns amongst users. We make this practical using a set of techniques which we call Oblivious Logging and private notifications. And we're able to show in the paper and later in this talk that the system can perform with 3 to 4 orders of magnitude better performance than the closest related work. Now, our security goal is that of indistinguishability. In the paper, we formally define this called access sequence indistinguishability. But informally, what that means is that two access sequences, usually consisting of reads and writes, of arbitrary length from a client should look indistinguishable to the adversary. What I mean there is that a user could be idle, a user could be sending random requests, a user could be communicating with a specific user. All of those instances should be completely indistinguishable from our threat. Now, to give you an intuition of what this is ultimately going to look like in our system, periodically, all users are going to need to send random noise at a predefined interval. And if you can embed real requests in this schedule that look like randomness, regardless of how many requests are legitimate versus dummy, that should, at a high level, achieve our security goal. Now, let's compare that to some of the other related work in the privacy space. We have a lot of systems that are designed with the security goal of k-anonymity, for example, or differential privacy. These security goals actually leak data by definition. So for example, in the case of k-anonymity, maybe in a particular round of messages, we don't know which of the k users in this subset has sent a particular message, but we do know that it's one of this k out of that is a subset out of the entire set of, let's say, end users. So every message actually leaks a little bit of data at a time. Our goal is to focus primarily in this space of indistinguishability, of which there's been a lot of really great recent work, but up until now has been generally prohibitively expensive, as we'll show in some of the comparative analysis in our experimentation. Our goal is to be able to port the security goal of indistinguishability, but with practical systems goals as well. So we want to be mobile friendly. We want to be able to be used by arbitrary applications where there's thousands or tens of thousands of users sending messages maybe every few seconds. We want to be with general purpose, so to be able to support not just chat applications, but also things like news feeds and social media and gaming and all sorts of other things. And we want it to have reasonably low latency. something that we would expect across a cellular network or a mobile network. Now, to describe our threat model, we do use the anytrust threat model. And so what that means is that while the clouds that we end up using are all potentially malicious, logging everything that there is to be logged about user requests, including source and type and destination, etc. We do assume that there are a number of different cloud providers from different countries operated by different organizations. And the application can be configured with at least 2, but probably on the order of 4 or 5 different clouds. And we assume that not one adversary controls all of the cloud systems. In other words, there's at least one non-colluding service provider who may be malicious in themselves, but is not colluding with all the other cloud providers in order to de-anonymize the users. Now, to flesh out the threat model a little bit more, Talek is designed to work amongst small groups of trusted users who trust, the other users within the group. But of course, the groups themselves are mutually distrusting, and as we would expect in any web service, there are a number of other users on the internet who may be attacking the service itself or honest users. Now, without going into a lot of detail, largely Talek focuses on a set of techniques which we call Oblivious Logging, which enable servers to operate on what seems like noise to deliver group messaging functionality in a way that still provides practical performance. And we'll defer more details on that in the paper. But at a high level, what Oblivious Logging does, it needs to be able to solve a number of different questions, including how do we bound the cost of expensive operations, such as PIR or private information retrieval. In Talek, we do use private information retrieval to retrieve a set of messages without revealing to the server which messages that we're interested in. We have to answer how do we write in a way that looks random to the servers. And if we write in a way that looks random, how do subscribers still find the messages that they intend to receive? We have to manage how do we deal with write conflicts when 2 users are trying to write to the same place. And we do have to provide some mechanism to achieve consistency in order to provide a coherent service across the variety of different set of service providers. Ultimately, what we ended up building looks a little bit like this. There is a library, which we call libtalek, that you can link to any arbitrary application. And that exposes an API that allows the application to send a message or subscribe to messages on a particular thread or group. libtalek will manage the write queue of honest writes as well as the read queue of honest reads. That read queue, of course, is informed by a set of topics or logs that I've subscribed to. And it will manage sending messages on the network to appear indistinguishable from noise. So at this point, we'll skip ahead to some of the results, and we'll defer to the paper to get a better understanding on exactly how this protocol works, the formal specification, as well as a formal proof as to how it achieves our security goal. So compared to previous work, we've implemented a set of head-to-head comparisons with Pong and Riposte, and we do show that for read and write workloads, when plotted on a log scale, as you see here in this graph, we do achieve 3 or 4 orders of magnitude better performance than some of our closest work today. So if you take a look at something like Pong, especially as you're reading messages that are getting bigger and bigger, the performance difference is pretty stark. Now, Pong was designed for a stronger threat model than us. It was published back in 2016 at OSDI, and instead of using the anytrust threat model that we use, it does not rely on any assumptions of collusion, and so all the servers could be colluding and malicious, and they can still provide the same security goal, which is pretty amazing. That comes at the cost and the trade-off of using a more expensive form of PIR, which is computational PIR, which ends up being much more expensive, and ultimately also has higher network overhead, as well as being less efficient on the server. We also compared to Riposte. While it's not exactly a group messaging protocol, it was designed for anonymous broadcast of messages. It has the same threat model as us, so one of anytrust, but instead of focusing on sending messages amongst a group, the protocol is just an anonymous broadcast system. So there's not even a read protocol that's specified in the paper. And the authors describe it roughly as PIR in reverse. And they also have, much higher costs than we do. And one of the things that we take advantage of is our workload. Using Oblivious Logging and shared secrets, we can achieve much higher write performance compared to Riposte. Maybe one of the more interesting results is that we show that we can have pretty practical performance. So in this experiment, we had a set of clients simulating a chat workload. These are clients that are simultaneously reading and writing actively against a service, sending messages and receiving messages every 5 seconds. And we show that we can achieve pretty practical throughput for this set of simultaneous users. Of course, it's going to be bottlenecked, and ultimately the bottleneck for performance for our system is PIR, or private information retrieval. The operations end up taking, each PIR operation requires a scan of memory, and so that ultimately ends up being a pretty hard limit for the performance of the system. But even so, by showing that we can support tens of thousands of simultaneous users, we're confident that this can potentially be practical for small to medium-sized messaging services, because ultimately, if you can support tens of thousands of simultaneous users, you can usually support much higher numbers of daily active users and even higher numbers of monthly active users. Of course, that's completely dependent on the workload and how engaging and how often users come back, depending on the workload, but we're excited about this result, and we're hoping to apply this to further applications in the future. Now, we've implemented this in Golang. We have a CPU version as well as one that's accelerated by the GPU. We encourage you to take a look, and if you have any questions, please reach out. Happy to answer any questions. Thank you.